Okay, hello again. Today we're going to be talking about acceleration. This is the beginning of our chapter 3 in our textbook. So we're going to be talking about accelerated motion. And so what we're talking about here is acceleration occurs when there is a change in velocity. So for instance, if you're at a stoplight, your velocity is 0, you're not moving. And all of a sudden the light turns green, so you're going from 0 velocity to maybe 10 miles per hour. So you have a change in velocity from 0 to 10, therefore your car is accelerating. We also have the same situation, say you're going 40 miles an hour down Wickham Road and all of a sudden you have the red light ahead of you, you're going to put your brakes on and you're going to go from 40 miles per hour to stopping at 0. So once again, you're going to have a change in your velocity. And this is what acceleration is. Okay, well, how do we know something's accelerating? We know something's moving its position or it has a velocity because you can see it moving. But sometimes it's hard for us to see something that's accelerating. So what I like to do is try to visualize yourself, picture yourself inside of that object that's moving, and will you feel the acceleration? So for instance, if your car is moving and all of a sudden you slam on the brakes, you can feel it inside. And that would be an acceleration. That same feeling you feel going up and down an elevator. So you can feel your stomach drop, or on a roller coaster. These are accelerations that you can feel. So a lot of times we refer to acceleration as something that you can feel. Well, how does it look on a motion diagram? Well, over here we have these red dots are going to be our motion of our object. And you can see that it's starting closer together and they're getting further and further apart, which means they're covering more distance over the same amount of time. So in this case, this object is speeding up. This one over here, it's covering more distance. It's getting smaller and smaller and smaller and less distance. So in this case, the object is slowing down. So speeding up and slowing down is just another word that we use for acceleration. Okay, well, there's a big difference between average velocity and velocity, or we talked about velocity and speed. Well, over here we're going to be talking about the average acceleration versus instantaneous acceleration. Well, the average acceleration, just like anything that you take the average over, it's over a range of numbers. Well, this is over a range of time, where instantaneous acceleration is over a specific point in time. So instance here is average acceleration is a change in velocity during a set change in time. This is an amount of time or a range of time. Okay, so here's a car starting at T1, sometime later, a delta T, it's at position T2, so that would be our average acceleration. Where instantaneous is a change in velocity during an instant in time. This is at this time t, what is its acceleration? And you would figure out, well, how much velocity has been changing during this small amount of time, and what is the time? Put this down here. So what does it look like on a graph? Well, just like here where we have our position time that we did last week in last chapter, now we have velocity in time. So our position time, this purple line here, is just showing us that over time it's changing its position. And we learned last week that the velocity average was just the slope of this line. And the slope of this line is our change in our vertical position here, which is change in x over change in t, which is the slope of the line. Well, now if we go over here and we have velocity over t, we can say that our acceleration average is just our change in velocity over our change in time, which once again is the slope of this line. So we know that our velocity is the slope of our position time graph, and our acceleration is the slope of our velocity time graph. So we can tell whether our velocity is positive by the slope, and now we can tell whether our acceleration is positive or negative also by the slope. Okay, so let's try an example. Okay, example 1. Describe a wind-up car's average velocity and its average acceleration is shown below. Well, first off, here's our graph. This is our velocity time. Time is measured in seconds, velocity is measured in meters per second. Well, right now I can look at the slope of this curve is negative, so that'll tell us right away that the slope of the velocity time curve is this acceleration. Acceleration is negative. That means that it's slowing down. Okay, so let's get an actual number for that. Well, the average velocity is your the average acceleration is your change in velocity over change in time. Our change in velocity is our final velocity minus our initial velocity over our final time minus our initial time. So here I'm going to plug in numbers, and it really doesn't matter which numbers you choose because the slope of this line is constant wherever you choose. Now I chose between 13 and 11 seconds. So I found out that at 13 seconds, I went over here and my velocity is 0.07, which is 0.07. And at 11 seconds, I found out that my velocity is 0.11. So here's the 0.11. And my change in time is the 13 seconds and the 11 seconds. So if I calculate it by my calculator, I do 0.07 minus 0.11 divided by 2, which is 13 minus 11. And I end up with negative 0.02. This negative tells us we have a negative slope. It means that this object is slowing down. Well, what about its velocity? So now we're going to go back to the velocity of this curve here. We know that this velocity is getting less and less and less, so it's slowing down. So it is a larger velocity early on, and the velocity is decreasing. Whoops. Okay. So now what we're going to do is we're going to talk about what is the sign of the acceleration. Let me go get a marker. Whoops. Sorry about that. Okay, so we know that we have our sign of our position. If we have a positive position, then we are to one side of the origin. And if we have a negative position, then we're over on this side of the origin. And we know that our positive velocity means that we're moving in that direction, and a negative velocity means we're moving in this direction. So our issue now is, what does the sign of the acceleration mean? So velocity and position are very straightforward. Positive is positive and negative is negative. But acceleration has a little trick to it. Okay, so first off, I have a chart here, and we're talking about the direction that it's moving. Okay, so let's just say it's moving in the positive direction, which means it's moving that way. And let's find out, is it speeding up or is it slowing down? We're going to try all of these things and come up. Let's just say here that it's speeding up. So we have an object that's moving in the positive direction, getting faster and faster. Well, positive times a positive is a positive. So this means that our acceleration is going to have a positive sign to it. Now let's look here. It's moving in a positive direction, but now it's slowing down. So we're moving this way, but we're going to be getting slower and slower. This means that a positive times a negative is a negative value. Our acceleration is negative. Okay, now here comes the difference. And this kind of makes sense to a lot of people, that if you have a positive acceleration, you're getting faster. If you have a negative acceleration, you're getting slower. Well, here's the trick. What happens now if I have an object that's in the negative direction, meaning it's moving this way, but it's speeding up? Well, you have a negative times a positive, you're going to have a negative acceleration. So there's two situations that are going to give us negative acceleration. One is you're moving in the positive direction, slowing down, or you're moving in the negative direction, speeding up. Both of them will give you a negative acceleration. And then the final situation is you have a negative direction, so it's moving this way, and it's slowing down. So we have a negative times a negative, which gives us a positive. So once again, we're going to have two situations that give us positive and two situations that give us negative. So we can have a positive acceleration if we're moving in the positive direction, speeding up. We can also have a positive acceleration if we're moving in the negative direction, slowing down. So this is something that you need to get comfortable with. It's a little bit more different than velocity and position. Okay, let's try 2 more examples. Okay, example 2. We have a car that brakes. Right away, the word brakes means it's going to be slowing down. So we know we're going to have a negative acceleration. A car brakes from 25 meters per second to 16 meters per second in 2 seconds. What is the acceleration of the car? So we're going to start with our formula here that the average acceleration is just our change in velocity over our change in time. Well, our change in velocity is the final velocity minus the initial. Here it says it's braking from 25 to 16. So 16 is our final velocity. 25 is our initial velocity. So we have 16 minus 25. And the change in time that this change in velocity takes place is 2 seconds. So we have 2 seconds minus 0. So we end up with negative 9 over 2, and we end up with negative 4.5 meters per second squared. What this tells us is that this acceleration is negative. So back to that other slide, we are moving in a positive direction, slowing down. Gives us a negative acceleration. Okay, we can also be moving in the negative direction, speeding up. But because we know we're going from 25 to 16, we know we're slowing down. Now example 3. We have a cyclist traveling at 5 meters per second. That's its velocity. It accelerates with an average acceleration of 1.5 meters per second squared for 5.2 seconds. What is her final velocity? So once again, now this one's a little bit more involved. So I'm going to write here our given. We are given the initial velocity of 5 meters per second. We're also given the acceleration of a positive 1.5 meters per second. Oh, this is a meter per second squared. We also know that the change in time for this change in velocity is 5.2 seconds. And what we're looking for is the final velocity, which is VF. Okay, so I know the equation I'm going to use is that my average acceleration is change in velocity over change in time. So I'm going to do a little bit of rearranging here. I'm going to cross multiply around here, and I'm going to say that my average acceleration times my change in time equals my change in velocity. But remember, the change in velocity is your final velocity minus your initial. So right here we have final velocity minus initial velocity equals average acceleration times change in time. Well, we're not looking for this whole thing. We only want to know this value here. So we're going to add initial velocity to both sides. I added it here. So now I have V initial plus A average acceleration times the change in time equals my final velocity. This is the equation that I'm going to use. So I'm rewriting it right up here just to make it easier with our unknown value V final equals V initial plus average acceleration times the change in time. Now I'm going to plug in all my numbers. I know that my V initial is 5 because that's a given value. I know that my average acceleration is 1.5 meters per second squared, and I know my delta t is 5.2 seconds. So if I plug in all these values right here and plug them into my calculator, I have that my V final is 12.8 meters per second. And once again, look at our units here, and we can see that here the seconds on top, seconds squared over here, that cancels out. We end up with meters per second, and we can add meters per second and meters per second, and we have the correct units for our final velocity. Okay, so that's the end of today's lesson. Don't forget the Edline assignment that goes along with this, and we'll see you tomorrow in class.